Good morning, everyone, and welcome to the special speaker series of the Simpson Center for Food and Agricultural Policy. The topic of today's online event is Produce More, Emit Less, Reducing Greenhouse Gas Emissions from Livestock Production. My name is Brandy Yanchik, and I'm an independent journalist and documentary filmmaker who is based in Edmonton, Alberta, which is in Treaty 6 territory. I'd like to acknowledge the diverse Indigenous peoples whose ancestors' footprints have marked this territory for centuries, such as the Nehayao, Cree, Dene, Anishinaabe, Saulteaux, Nakuta Iska, Nakota Sioux, Niitsitapi, Blackfoot peoples. I also acknowledge this as the Métis homeland and the home of one of the largest communities of Inuit south of the 60th parallel. Before I introduce today's panelists, a couple of quick housekeeping items. If you're having difficulties hearing the webinar at any time today, or you're experiencing an unreliable internet signal, you can always use the call-in number included in your webinar registration email, or by clicking the arrow next to the microphone icon and pressing switch to phone audio. There is a box labeled Q&A, and this is where you can pose your questions to the panelists. If you see a question in the Q&A box that you think is important to ask, you can also click the thumbs up icon on the question to move it to the front of the queue. We will also have a couple of poll questions for you. Today's event will consist of the presentations by our panelists, followed by some questions after each presentation. We will then have a panel discussion around the topic. Today, I am joined by three distinguished researchers for this discussion organized by the Simpson Center from the School of Public Policy at the University of Calgary. Dr. Tim A. McAllister is a research scientist in ruminant nutrition and microbiology working at Agriculture and Agri-Food Canada. Dr. John Bazarb is an associate professor in livestock genetics, genomics at the Faculty of Agricultural, Life and Environmental Sciences at the University of Alberta. And we have Dr. Gabriel Ribeiro, and he is an assistant professor and a Saskatchewan beef industry chair at the University of Saskatchewan. Welcome. Before we begin, we have a poll question for the audience. Average greenhouse gas emissions per head of dairy and non-dairy cattle in Canada are A, one of the highest in the world, B, around world average, C, one of the lowest in the world. You have 1 minute to answer the poll, after which we will display the results. Okay, we have our answers here, and 18% said of the participants think that greenhouse gas emissions per head of cattle in Canada are one of the highest in the world. 18% also of the participants think it is around the world average, and 64% of the participants think that these are one of the lowest in the world. Now I will briefly introduce the topic before inviting our distinguished speakers. In the 21st century, Canadian agriculture faces a pivotal mission to reduce greenhouse gas emissions, strive for net zero emissions by 2050, and simultaneously enhance productivity and the economy, all while continuing to feed a growing global population. Beef producers play a pivotal role not only in meeting the protein needs of Canadians, but also in exporting nearly half of their beef production. Our beef and cattle sector makes a substantial $24 billion contribution to Canada's GDP and supports nearly 350,000 jobs. However, there's a challenge in the mix. greenhouse gas emissions. Agriculture accounts for 10% of total greenhouse emissions in Canada, with animal production responsible for more than half of that share. In fact, animal production stands as the second largest source of methane emissions, just behind the oil and gas sector. The Government of Canada has set a greenhouse gas emission reduction target of 40 to 45% below 2005 levels by 2030, and reducing greenhouse gas emissions from animal production can contribute to achieving it. Here's the breakdown of greenhouse gas emissions in the agricultural sector. Livestock emissions make up 51% of these, and they result from two main sources: enteric fermentation and manure management. Out of the 35 megatons of livestock emissions, 70% originate from enteric fermentation. This is a natural digestive process that happens in the stomachs of ruminant animals. The other 30% come from manure. When we look at the types of gases emitted from livestock production, 81% are methane, and the remaining 19% are nitrous oxide. When we look at emissions by type of livestock, beef cattle are the major contributors with 72% of greenhouse gas emissions, while dairy cattle contribute only 15%. Now, if you look at the bottom line of this graph, you'll notice that emissions from beef cattle have seen a significant 24% drop since 2005. And this aligns with a nearly equivalent decrease in herd size during this period. In Canada, we've seen a significant reduction in heads of cattle since 2015. What's particularly interesting is that over the same time frame, emissions from dairy cattle have actually increased by 12%, despite a slight reduction in their herd size. Okay, so here's the answer to that poll question. When seen as average emissions per head of dairy and beef cattle, Canada is one of the highest emitters among comparative economies. This is because our cows produce more milk and require more feed intake. Hence, we generate higher greenhouse gas emissions. Similarly, average emissions per head of non-dairy cattle are one of the highest among comparative economies. Again, this is because our cattle are bigger in size, require more feed intake, and thus produce more emissions. However, when emission intensity is measured in terms of emissions produced per kilogram of live weight of the animal, or emissions per liter of milk yield, Canada boasts one of the lowest emissions intensities. This means our animal production is relatively efficient because of high feed quality and a low emitting animal waste management system, both of which result in lower emissions. Today, we're going to discuss the strategies that can be adopted to contribute to Canada's emissions reduction target of 40% below 2005 levels by 2030, when we have little room to play with already low emission intensities. We'll discuss options for mitigating methane emissions in Canada with a focus on Western Canada, effectiveness of different strategies that may vary according to production systems, and lastly, need for better communication of research to farmers and to the government to improve adoption of these mitigation strategies in farming practices. I will now invite Dr. Tim McAllister to start the discussion.
Thanks very much, Brandy. So you can see my screen okay, I hope?
Yes.
Great. All right, thanks everybody for the opportunity to share some work that we've been doing, as well as work that's going on around the world in relation to strategies to reduce enteric methane emissions from ruminant animals. I just want to start by recognizing my co-authors, Dr. Ludwig Guan at the University of Alberta, and Mimi Zhao, both at the University of Alberta, Graham Atwood with Ag Research in New Zealand, and Robin Anderson, who's with the USDA. This is very much a global problem, and one that needs to be addressed on a global basis, drawing out all the expertise we can find throughout the world. And as a result, we're collaborating with a number of different organizations in various locations. So as Brandy said, this is a huge challenge. We're looking at reducing methane emissions by 25% from 2010 levels by 2050. How are we going to achieve that? Well, one of it's going to have to be through increased sustainable production. So we're going to have to continue to lower the amount of emissions per kilogram of meat or liter of milk that's produced. We need to look at ways of directly decreasing methanogenesis, whether that be by lowering the amount of substrate that's available for methanogens within the rumen, or directly inhibiting methanogens themselves. And then we need to also look at reductions in food waste and possibly also moderating consumption in some cases, particularly in some regions of the world where the consumption of meat is higher than what's really needed to meet dietary needs. But we probably don't want to go to the point of looking at, I know there are those out there advocating going completely vegan. But if we look at some of the trade-offs at that's probably not a very realistic option and has many negative consequences as well that would be around that type of strategy from a policy perspective. So as I mentioned, this is a global effort. The Global Methane Pledge, which was in 2023, is led by the US and the European Union. There's about 150 countries that have signed on to that now with the objective of reducing methane emissions by 30% by 2030, so as to limit increases in temperature to 0.2 degrees Celsius. It already looks like original target was about reducing temperature increases to 1.5 degrees going forward. It looks like we're already not going to make that target. It's going to warm up more than that by 2050 for sure. So right now, the focus is on the energy sector where the majority of methane emissions take place, but there's increasing pressure for that to be reduced in agriculture as well. And that's why there's such an emphasis on that on a global perspective. Why is methane the focus? Well, it has to do with the duration of which these gases persist within the atmosphere. So carbon dioxide can persist for thousands of years in the atmosphere. So if we're going to lower carbon dioxide levels, the responses that we're going to see or the benefits as a result of that reduction are going to take many more years for realization because of the long duration of persistence of that gas in the atmosphere. If we compare that to methane, methane lasts about 12 years. And so if we can lower methane emissions as quickly as possible, then the benefits of that in terms of restricting the global increase in temperature will be a positive aspect. And that's why there's such an emphasis on lowering methane emissions on a global basis, both from the oil, gas, as well as agricultural sectors. So when we look at application of that in a livestock production system, what do we need to think of about in terms of a technology that's going to lower methane emissions? Well, we need to think of efficacy. First of all, we want to make sure that it actually works. And there's lots of things out there that are being touted that will lower methane emissions. In fact, they don't work. The cost, it can't be so cost prohibitive that it makes us economically uncompetitive in terms of the production of the protein that humanity requires. It needs to achieve regulatory approval, so it can't pose any threat to the animal, the environment, or the humans upon consumption. It has to be a technology that will be adopted. Developing an effective technology that nobody uses won't have any benefit either. It has to have consumer acceptance as well. And in some cases, that's not directly related to regulatory approval. Consumers can decide that they just don't want to purchase a particular product that was produced in a particular way, even though that didn't pose any health risk or economic hardship. If the consumers aren't going to buy it, then it's not going to have any kind of value in terms of a mitigation strategy. It also has to have longevity and consistency. It has to work across a very wide variety of production systems, and it needs to be compatible with the production system that it's being employed in as well, making it necessary that we often need regionally specific mitigation strategies if we're going to achieve reductions. Now, when we look at strategies for lowering methane production, there's essentially 5 ways we can do it. One is through lowering the production of hydrogen. The microbes or methanogens take hydrogen and they use it to reduce carbon dioxide to methane. So if we remove hydrogen or reduce the amount of hydrogen that's produced, we can lower the amount of methane that's produced. We can also use direct methanogen inhibitors, which target those specific microbes in the rumen that are responsible for methane production. We can look at alternative hydrogen sinks, so we can end up having that hydrogen go to some other source other than the production of methane. So that's also being looked at as well. We can look at increasing the productivity. So by increasing either the amount of milk production or the amount of meat that's produced, the average daily gain, If we do that in a manner without increasing emissions, then we're going to improve that intensity value and lower it even further. And then finally, we can also look at oxidation of the methane as well. Now, there's several different types of methanogens in the rumen. This is 13 species that I've listed here. These are ones that are actually culturable in the laboratory. There's probably many other species of methanogens in the rumen that are not culturable in the laboratory and are yet to be identified. If we're going to lower methane emissions, though, we need to make sure that we target all of these species. If we only target a subset of those species, then there's a good chance that those that survive will fill the niche that's been vacated by those that were inhibited, and we'll end up with the same amount of methane production as we originally had prior to the addition of the mitigation strategy as a result of adaptation of those methanogen populations. Now, those methanogens exist in specific compartments within the rumen itself or within that stomach. Some of them, as they can show up under the microscope in terms of that they've got enzymes in them that emit a specific wavelength of color, so we can see them under a confocal microscope. Some of them exist in the fluid and associated with feed-associated bacteria that are digesting the feed. Some are associated with protozoa, both inside and outside of the protozoa. And part of the reason they do that is because the protozoa and the fungi have these organelles that we call hydrogenosomes, which produce hydrogen that those methanogens can use as a substrate to produce methane. So what are some of the emerging mitigation strategies? Well, there's a whole lot of them that are being developed right now, many of them that have been tested, but very few that are backed by solid scientific evidence in terms of a lot of publications that support their use. Right now, the leading additive is probably 3-nitrooxypropanol, or 3-NOP as it's known as. It's a product known as Bovaer. It has a lot of studies out there that show that it's quite effective in terms of lowering methane emissions when it's administered to cattle. There's also a lot of work going on various plant bioactives, we call. Some of those are called essential oils or tannins or saponins. Most of those work by reducing the amount of hydrogen that's produced in the rumen. When that happens, one of the key things we've got to watch out for, though, is that that doesn't result in an overall lowering of digestibility of the feed, and as a result of reduction in the production, whether it be the amount of meat or milk that's produced by the animal itself. We don't want to use mitigation strategies that lower overall productivity of the animal as a means of reducing methane emissions. They also have some challenges as well in that they're really non-specific in terms of their antimicrobial activity, so they really don't target the methanogens directly. There are numerous sources that have been tested, but most of those have been tested in the laboratory. Very few of them have been actually tested in the animal, and often when they've been tested in animal, the responses that have been seen have not been near as great as what was originally seen in the laboratory. There's many different commercial bends. Their compositions can change. It makes it difficult then to predict when they're going to be effective and when they're not. Asparagopsis taxiformis, this is a seaweed that you've heard so much about that was originally developed and researched in Australia. It relies on an active compound called bromoform, which inhibits the methanogens directly. But it's also been shown to be a carcinogen. So there's some issues probably from a regulatory perspective with regard to the use of seaweed. Reductions have been as high as 90%, but there also appears to be some issues with regard to the stability of the bromoform in the seaweed after transport as well. So some additional things that need to be looked at there. There's also research going on at looking at alternative ways of producing the bromoform in other platforms, such as in yeast as an expression system to produce that compound. And it can also be chemically synthesized as well. I already mentioned about 3-nitrooxypropanol or Bovaer. It's now commercially available in a number of different countries and has gone through the regulatory process, including the European Union, Brazil, Chile, Mexico. There's quite a few different countries now that are approved to use 3-NOP as a method of mitigation. Not a lot of word out there what the adoption of that has been. There is some use going on, but it's definitely not widely spread throughout the entire industry. There's more than 50 studies that have supported the effectiveness of that. The variability is anywhere from about 20% reduction to 80% reduction. That reduction tends to be greater in animals that are fed finishing diets. So higher grain diets, which actually have lower emissions than what's associated with a forage-based diet on an intensity basis. Few studies have looked at the long-term responses to that, whether that remains effective, for months after administration as well. The other limitation is that at this point, it needs to be administered through the diet as well to be effective. There are also other nitro-containing compounds in various forages that could be explored as a method of lowering methane emissions. So some of these compounds could also directly inhibit methanogens or act as alternative electron acceptors. So that's an area that there's some studies going on as well. But we also have to be careful because some of those are toxins as well and can have negative effects on animal health from that perspective. There's also the approach of probiotics, which is basically administering bacteria into the digestive tract that will inhibit methanogens. That may be either through direct inhibition of the methanogens themselves or inhibition of those bacteria that are producing the hydrogen that the methanogens use as a substrate. Getting specific activity so that it's not a general inhibition of the whole population again is another issue with this approach. And stability and establishment of these probiotics when they're introduced into that competitive rumen ecosystem is another challenge that this technology is facing. There was a lot of advancements made after they sequenced the entire genome of the first rumen methanogen. That enabled for various genes then to be looked at to identify chemical inhibitors that could be used to specifically inhibit methanogen species. It also led to the identification of surface proteins that are on the surface of methanogens that could be used as vaccine development. So New Zealand has a very large program going on in vaccine development, which involves in vaccination of the animal and the immunology of the animal, the production of antibodies that are specific against methanogens in the rumen as a way of lowering methane emissions. So we need to make sure those antibodies are stable in the rumen, that they target cell surface proteins, that they have the proper adjuvant, and that they contact all methanogens that I mentioned within those various ecosystems. If any of those methanogens go untouched, then there's a chance that the methane emissions will return to pre-treatment levels after vaccination. There's also looking at phage, which basically just attack the methanogen. There are viruses that could kill the methanogen directly by causing lysis. We know these exist, but at this point, there's no phage that's been isolated in the laboratory for this purpose. There is some that are integrated right into the genome, and there's enzymes that have been looked at that are produced by those that can be used as for lysogenic to lyse them as well. Methanotrophs are bacteria that actually oxidize methane after it's produced by the methanogens. So that's another possibility, although it doesn't look like they're very competitive within the rumen. They occur within natural ecosystems, like in peat bogs and sloughs and areas like that, but they don't seem to be very active in the rumen itself. So whether this is a valuable method to stimulate the population that's there in a way of increasing methane reduction is still an unknown. At this point, even when we lower methane emissions, we don't see a change in these populations. And then finally, another approach is actually oxidation outside of the animal itself. So this is a technology that's been developed in a company out of the UK called ZALP. And what it is as the animal breathes out the methane through its nasal cavity, that methane enters into a system where that methane is oxidized to carbon dioxide and water. And then that way the methane probably results in about a reduction of about 70%, because about 70% of the methane comes out of the nasal cavity, with the remainder either coming out directly out of the mouth or out of the hind gut. So maybe a 70% reduction with that technology. Obviously, it's got to be used in an environment where the animals can move around with that device. What are the advantages of it? Well, there's no risk of adaptation of the microbial population within the rumen. It can be used, they're advocating that it can be used in all intensive farming systems. I'm a little bit skeptical as to how much it could be used in an extensive range system with our types of rangeland production systems. It does provide traceable levels of methane reduction, so they can measure how much methane is reduced by looking at the level of oxidation, and it provides additional health, nutrition, fertility, and other measurements because GPS and other types of animal behaviors information is conducted. And then finally, just a little bit about emerging molecular approaches to inhibiting methanogens. There's a number of technologies. You've probably heard of CRISPR-Cas, which was awarded the Nobel Prize a few years back. There are other technologies that we're looking at that we can directly regulate the genetic activity of the methanogens through these mechanisms. And basically, we need to develop delivery systems for those as well. So what are the next steps in inhibiting methanogens? Well, we really need to pull out all the stops and use all the approaches that I've talked about today, because it's such a huge challenge. We really need to look at all the technologies that can be used to hopefully achieve those objectives in terms of methane reduction that have been set on a global scale. So with that, thanks for attending. And I think I have a bit of time for questions, maybe Brandy.
That was fantastic, Tim. Thank you very much. Just to our viewers, if you have any questions for Dr. Tim McAllister or throughout any of our panelist presentations today, please submit them using the Q&A box. And we love to know your name and where you are from. So we have a question for you here, Tim. You suggested using a combination of approaches. When we talk about sustainable intensification, the main motivation is higher beef or milk yield and profitability. Could the adoption of genomic technologies and use of higher quality feeds have significant economic implications?
Yeah, they certainly could. And you know, really, in terms of what's at our disposal now for immediate implementation in Canada, that is the primary way that we can. So by improving feed quality, that lowers the amount of methane per unit of milk or meat production that takes place. Why I said the other thing is that we need to realize that not all technologies are going to work across all production systems. And that's why we need, you know, production specific mitigation strategies as well. But in terms of lowering methane emissions now, and that has to be done, you know, if we basically a lot of that is through improving feed efficiency. And if we improve feed efficiency, that also leads to improvements in profitability, regardless of whether it alters methane emissions or not.
Okay, thank you very much, Tim, for answering that question and for your wonderful presentation. We're now going to move on to our next speaker, Dr. John Bazar.
Great. Well, thank you, Brandy. Am I coming through loud and clear?
Yes, looking great. Thank you.
Great. So thank you. And Tim, thank you very much for that, that great background. That saves a lot of time. So really, I want to talk about the breeding genetics and genomics component of reducing greenhouse gases. And I'm going to, of course, start off with our favorite animal here, our methane-breathing beef cattle. And I just want to put some things in context, of course. You know, I mean, livestock production is 14.5% of global man-made GHG. And Canada's livestock is about 5% of Canada's GHG. What we should remember, though, is that, you know, livestock production and agriculture, you know, particularly livestock production, produces high quality protein, a lot of jobs and community development. In this case, $40 billion to GDP each year, while, you know, the grass and the legumes and the rangelands that are growing, you know, where cattle are sequestering carbon, improving soil quality, biodiversity, water quality, all of those things. So we've got to remember that when we talk about sustainable agriculture, that there is more to it than just a carbon footprint. There's, you know, community development, there's animal welfare, there's, you know, the advancement of advancing technologies, all of those things. Just some numbers. I know this whole business about carbon credits is kind of like a numbers game, but just so that you remember, Canada's agriculture is about 69 megatons, so that's million tons. Canada itself is 678 megatons, and globally it's 46,000 megatons. So be careful not to mix up the megatons. That's millions of tons, so it's quite a bit. I think I want to draw your attention to another major event that's occurring. I think many of you would recognize this photo. It's from one of the wildfires. This was around Kelowna. And this year, and this is very conservatively estimated, that wildfires in Canada released 2,000 megatons, at least 2,000 megatons of CO2e, and those fires are still burning and likely to burn, some of them throughout the winter. This is 3 times more larger than the country's annual GHG emissions, and 29 times higher than agriculture. However, I mean, it isn't all bad news. We've got grasslands that have the ability to store an additional 119 megatons. So that's just putting things in perspective, and I wanted you to share that with you. When it comes down to mitigating practices in breeding and genetics, well, we already do some great things, right? I mean, right now, as common practice within the cattle industry, particularly the beef industry, there is a short breeding season, and we calve, or we breed so that we calve at 2 years of age. Of course, that reduces, or that improves production efficiency. One of the main mitigating breeding practices, animal breeding practices I want to talk about is, of course, increasing or optimizing herd or cow hybrid vigor. This is really genomic diversity. Want to talk about feed efficiency through residual feed intake, and then all of the molecular breeding values that us and others like Livestock Gentech produces that can be used by the ranching community and the dairy industry to improve their production efficiency and reduce their carbon footprint. And then I want to end with a little bit on novel traits like actually finding molecular breeding values for methane emissions. The reason we can do this here in Alberta really well, and with livestock specifically in the University of Alberta, is over the last 20 years, we've developed a very large reference database where we have many, many detailed phenotypes and many genotypes, even full sequences for traits that are important, such as feed efficiency and fertility in cows. And we also have similar types of genotypes and phenotypes for methane traits as well. The other thing we can do is that with that reference database, we can actually determine the genomic breed composition of our animals. In this particular cube that I've got displayed here, you can see how we can, with gene frequency, we can essentially separate out breeds very nicely. And we can use that to determine the breed composition of crossbreeds. In this second cube that I've shown you, all of those pink dots in the middle are essentially crossbreds, and we can determine what the breed composition is of those crossbreds. The reason that's so important for us is that determining the breed composition of an animal relates to its genomic diversity and the amount of heterosis or hybrid vigor it's containing. The reason we can't do that with pedigree in the beef industry is that the beef industry doesn't keep pedigree. And in addition, even if we could keep a perfect pedigree, Mendelian sampling and genetic recombination mixes everything up. And so when we determine the genomic breed composition of an animal, we can determine its genetic diversity. So for example, in this case, this looks like a Angus animal, purebred Angus animal, but it's not. When we look at the breed composition, the genomic breed composition, you can see it on the left-hand side of your screen. It's got a fair amount of Simmental in there and a Charolais, and it has a hybrid vigor score of 55 or 56%. And that relates to, and you'll see in a very quick bit, it relates to the fertility, the production efficiency of that animal, which will reduce its carbon footprint. Questions were asked about economics. Here we've plotted sort of a 6-year timeline in terms of what happens with a high vigor herd and a low vigor herd. And you can see that the accumulative net income moves up really nicely in our high vigor herd, so that replacement heifers are earning, you know, $160, $61 per female more per year than a low vigor herd. So that's excellent. When it comes down to, you know, a life cycle analysis of a high versus low vigor herd, you can see here very nicely that when we keep the hybrid vigor up in our herds, we actually reduce the overall carbon footprint, so that it ends up, you know, on a, if we could apply this to the full Canadian beef cow population and bred heifer population in beef cattle, it would equal about 300,000 tons of CO2e per year, worth about $16 million. So that's very encouraging. The other thing we've done, of course, with our databases is we've developed molecular breeding values for many traits and produce selection indexes. Here, this is a selection index for replacement heifers, and it includes both retained heterozygosity, which is you know, an indicator of heterosis or hybrid vigor, and then a whole pile of traits, including feed efficiency. The word residual feed intake is our measure of feed efficiency. And so that this will allow us to not only improve genetically the production efficiency, but also reduce GHG and methane. Similarly, with our feeder cattle, we have a feeder profit index. Of course, this also has a very high weighting for residual feed intake, which is feed efficiency. And I want to say that many breed associations have breeding values that can be used and indexes that can be used to improve feed efficiency. This is just one I'm showing, because this is one that was developed by Livestock Gentech from the University of Alberta. So looking at this from a, you know, what is it going to do? You know, I asked the question, do low RFI cattle, that means efficient cattle, eat less and produce less methane? And of course, the answer is yes. There are many, many publications on this. And I'm just going to show you an example. Here's a feeder cattle operation, a feedlot operation that produces 16,000 feeder cattle. If they select for feed efficiency at a genetic response of 0.8% per year, they can save over 500 tons of barley. And a cow-calf, large cow-calf operation could save, you know, 50 round bales. And when you calculate that all out, you know, it will have quite an impact on reducing GHG and the carbon credits and the tons of CO2 saved per year at the bottom. The very last point I want to talk about is novel traits. And in this case, I'm talking about methane emission. And of course, we can measure methane emission using, there are many methods, and other presenters might discuss them, but we use the green feed emission monitoring system, or the green feed system, and we can measure methane from animals outside, both methane and CO2, outside, on pasture, and in dry lot. Summer, winter, we have experience with that, so it's very good. On the right-hand side of the slides, you can see that there's some squiggly little lines there. The top is CO2 and the bottom is methane. Those peaks at the bottom in the red line, those are methane emissions from burps or eructations. And the very, very low level you might see at the very bottom, there's a little line there at the bottom. That is background level coming from methane respired from the lungs. So it comes both from respiration and burps, eructation. Methane emission, of course, is a really tough trait to measure, expensive. And so we're also looking at fecal NIR, near infrared, as a indicator trait. And it is possible to come up with a molecular breeding value for methane emission, which has heritability of at least 30%, and I'm sure that we can get an accuracy above 35%. So that's really good. So in summary, I'm going to just talk about some barriers. When I speak with producers and public, there is the perception and the connotation that Canada's agriculture is a very small contributor to global GHG. And I guess if you look at all the numbers, you can, just from a numbers point of view, you can see that where that perception comes from. Also, there's the feeling that climate change is here and it will continue a long time. So we must have two strategies, two broad strategies to deal with this. And one should be mitigation, no doubt, what we're doing now and all the things that Tim talked about. And I'm sure that others will talk that way too. But we also must be able to adapt our infrastructure and our systems and our plants and our animals to a changing environment. Carbon price is too low to be an incentive for practice change. It's at $50. Lots of people think that's too high, but when we model it in terms of, will a methane trait replace one of these other production traits in a multi-trait selection index, the price of carbon has to be in the area of $750 a ton. So that's really, really, really high. Cost of practice change is risky for producers and often too high. And so we've got to find a way, a policy way to incentivize, for example, producers, particularly beef cattle producers, to use genomic tools and to have their animals genotyped. Also, often within the beef cattle sector, I won't say the same for the dairy and other livestock species are very good when it comes down to the use of breeding values. In the beef cattle industry, breeding values, here I say EPDs, those are expected progeny differences for feed efficiency or for fertility traits, have very low accuracy, and they are they're missing. We just don't have them. In addition, there are no EPDs for a methane trait, and so that's something that needs to be worked on. When it comes down to getting an incentivization or aggregating carbon credits, the whole area in the animal sector is very burdened by record keeping. Every animal needs to be recorded, and all sorts of metrics about the animal have to be recorded. And so that causes a complete, a very, very difficult thing to do for aggregation of carbon credits. And finally, and I know Tim probably might have mentioned this, but when it comes down to some of the feed additive things, and to the cow herd, there's a variable dose response. In other words, some cows and some animals like their daily treats of the feed additives, and others do not. They just don't want to take it. So that becomes a very, very strong barrier for adoption of some of these technology. So with that, I'd like to end and open the discussion to some questions.
Thank you so much, John, for your wonderful presentation. We have a question for you here. You showed that high hybrid vigor and low residual feed intake are correlated with lower emissions, and these are determined by genomic data. What is roughly the adoption rate of these genomic technologies among Canadian cow-calf producers, please?
Yes, so very low. So one of the issues that we have, particularly on the beef cattle side, I'll mention that because that's where the biggest contributor to greenhouse gases are. Only about 20% of beef cattle producers use genomic technologies, and that has to come up dramatically. So that's the kind of the bad news. The really good news is that over the last year or so, veterinarian service providers have been seeing a very large demand for genomic technologies. So there is a chance that if we can incentivize the beef cattle producers, that they will take on these technologies in an increasing rate. When it comes down to the other livestock industries like dairy and pork and poultry, their use of genomic technologies is very high. It's very good. And so they can act as a, uh, the people to go first and the rest of us, they are the innovators, and the beef industry can learn from them.
Well, thank you for answering that question. We will continue the discussion with the experts in our panel discussion. For now, it is time for our next speaker, Dr. Gabriel Ribeiro, to share his insights. And again, if you have questions for the panelists, please remember to put them in the chat because we would love to hear from you. Thank you.
Okay, good morning, everyone. I hope you can hear me well.
You sound great.
Okay, great. We heard two really good talks so far. I'll try to add a little bit here to what Tim and John have already said, and try not to repeat too much and bring something new to the conversation. And also touch a little bit on some of the work we have been doing that I have been involved here at the University of Saskatchewan. So my focus is in beef cattle production, so I'm a bit biased on the beef side of things, so don't take that against me. So just before we get into deeper in this conversation, I think sometimes we forget that we're talking about food production here, about a very nutritive food that's quite important in the diet and brings a lot of value, right, to our diets. And ruminants in general, like cattle and other ruminants, have the ability that no other animal, I think, have in terms of being able to convert these low quality forages or fiber or byproducts into high quality food like beef and milk, right? And when we look at where we have the feeds that we're using and where the cattle is, usually we're not really competing for food with humans, which sometimes that's forgotten on the conversation. So just kind of bring that to the conversation, make sure we are thinking about those things. Getting more into the deep of the rumen itself and the fermentation and the methane production, it's just like a quick diagram of what's happening in the rumen. So as animals eat and they get a variety of different feeds, right? They have carbohydrates, protein, lipids there. That feed gets into the rumen. The carbohydrates and protein, mostly they get digested in the rumen by the microbial population, as Tim kind of mentioned. It went over a little bit this slide, these fermentation pathways. But they break down those carbohydrates or protein sources. They can ferment that to volatile fatty acids, which is these compounds here in the bottom, and they actually use that for animals actually use that for as their energy source. So that it's quite important, and that fermentation process is quite important. So ruminants can use like fiber, right, through that fermentation, which monogastric or non-ruminant animals can't do that well. So if we have a fermentation that's more on the propionate side, we get less methane. If it's more towards acetate, we get more methane because of there's more hydrogen that's released for methane production. So the problem is with more forages, usually we get more acetate production. The problem we have is if we try to knock down methane and eliminate methane, is we might also reduce that fermentation, and that's not good for the animals. So we need to make sure when we are trying to change those pathways, we actually not inhibiting fermentation overall and production of animals. So we need to find ways for those hydrogen to be utilized in different ways so that fermentation is not reduced. When we look at the greenhouse gas in terms of beef cattle production, farm gate kind of emissions, we can see that definitely methane is where most of the emissions coming from beef production is. About 60% or so comes from methane. But when we look at the different sectors, the cow-calf compared to the feedlot of total CO2 equivalent emissions, most of it is coming from the cow-calf side because of the forages and how the feed that they get fed, right? The grazing systems, and because of they're kept for a long period of time, right? So the life cycle of that system. And that's going to be important for us to understand where those emissions are coming from, because that is also is going to affect how we focus our target in terms of reducing emissions, right? So just keep in mind that 80% of our emissions on the beef sector is coming from the cow-calf side. But before we get deeper into that, there's a really good study that I like always to remind people that was done a few years ago by a group in the US that kind of did a modeling work to see what would be the impact of removing all animals, like all animal production, not just cattle, okay? All animals, so poultry, swine, removing everything and replacing it with crop production, so kind of moving towards more a vegetable diet. And what they saw is that the total agriculture greenhouse gas reduction would be around 30%, 28%. But in terms of total US greenhouse gas emission, that would be just around 2.5%. So it's not that huge of an impact. And associated with that, they would have a huge problem in terms of achieving or feeding their population in terms of producing less essential nutrients. And they suggested that the amount of food that each person would have to eat would be so much that would be kind of not realistic. People would have to eat more than 2 kilos of feed to meet their nutrient requirements, and some nutrients like energy people would be eating much more than they needed, which is already a problem in terms of when we look at our diets in North America. We already eat much more energy than we need, right? So we need to think about what some of those ways strategies where that can take us. And sometimes we don't discuss enough, but when we look at the emissions from livestock, that's part of a cycle, right? So the grasses and crops, they are taking carbon from the atmosphere through photosynthesis. They're using that for their growth. They're bringing some of those carbons down through the soil. So and cattle definitely can through their fermentation can release some of that. But that's part of a cycle. When we look at fossil fuel industry, they take from the soil, like deep down, like those carbons that are stored really in a secure way. They bring that to the atmosphere, and that's not part of a cycle, right? So then it's quite different, and we don't kind of talk enough about that main difference. And on the top of that, a lot of those the carbon or that's released by fossil fuel is being used for the production of non-essential nutrients or products that non-essential for human. So when we look at like the strategies that we have to mitigate greenhouse gas emission in livestock or in cattle, specific in beef cattle, the most effective strategies we have is to increase, like Tim said, is to increase those production efficiencies, and that can be through genetics, through the diets, or the use of growth enhancing technologies. Definitely, we need to focus on promoting health and reduce mortality rates of your herd. Those have huge impact on this life cycle assessment and the greenhouse gas. So if farms have poor health and high mortality rate, that is going to really increase emissions. We can improve weight gains per unit of beef produced. And if we think on a cow-calf operation, really improving fertility, pregnancy rate, and making sure that every cow produces 1 cow per year is definitely going to be one of the best ways we have right now already to improve reduce our footprint, right, in the beef sector. So we did a few years ago a bunch of studies for over 4 years, feedlot studies looking at the impact of growth enhancing technologies. And we used those 4 years of feedlot work to kind of do a modeling study to see the impact of the technologies we have right now, like implants and ractopamine and others on not just on greenhouse gas, but ammonia, land use, and water. And you can see that compared to a system where you don't use those technologies, by using that, we reduce quite a bit greenhouse gas, ammonia, land, and water by up to 10% or more. And this is kind of like a very, like we put a big safety margin here. So in some situations, those improvements can be even greater than that. So just to show that those technologies we have right now that we use have a big impact on greenhouse gas, not just on greenhouse gases, but also on water and land use. And by not using those technologies, or if we decide not to go that way, we will increase our emissions. And it's something that we sometimes don't talk. We see like some companies going in terms of like fast food companies going towards like, oh, we're providing no hormone beef or no feed or no growth enhancing technologies. But the same people that think that it's better for them, that they go buy that, it's usually they usually don't want more greenhouse gas emissions associated with that product. But if they decide to buy that product, that's actually what they're going for here. Just kind of to bring that in mind, and just remind that those technologies we're using are safe for for the animals and for humans. So we have been using them for a long time, and we should be really careful if we decide not to use those technologies, because they will have consequences. This study here that was just published last year was a really interesting study. They did like a meta-analysis or a review of all the studies that have been done with ruminants on that try to reduce methane, and they did a meta-analysis to see what strategies is available. And then from 98 strategies that was available, they kind of grouped them in different strategies here, like related to animal and feed management, to diet formulation and ruminant manipulation. And they saw that from those, there was just 3 strategies that reduced product-based emissions, right? So per unit of beef or per unit of milk produced. And there was 5 strategies that had some impact on total emission by the animal, daily emission by the animal. So, but when you look at where they can be applied in this last portion here of the slide, you can see that most of those technologies can be applied on confined or confined situations, and just 3 of them could be applied on grassland systems. And when we look at where most of our emissions are coming from, which is on the cow-calf side, that is raised on extensive situations, then conditions, then we don't have a lot of strategies available for that system yet, right? Definitely increasing feeding level, decreasing grass maturity, or improving forage quality, using forages with tannins are the strategies that we have, and they have limited kind of like impact, right? When we look at the impact of some of those technologies, we can see that we can reduce then efficiency there, or emissions there in terms of per kilo of milk or beef by 12%. And with those other 5 strategies here, we can reduce that by about 17%. So as you see here, moving from a lower quality forage to a higher quality forage, we can promote huge reductions. We should always try to improve that and manage forages better, so we can improve the performance of animals, efficiency of the animals, but also reduce emission of methane. And as we move to more concentrate or mixed diets, we can reduce even more of that. However, we know that some of those strategies are not really realistic, depending on the sector, like the cow-calf sector. We are not going to be using high grain diets, right? But definitely moving to a more higher quality forage and managing better our pasture can have an impact. Also, fat can be used in some of those diets to reduce methane emissions, but again, we can't really do that very easily on an extensive system. We definitely have been investigating ways to supplement animals on pastures, and that there's more and more work on that area, but there is limited ability to do some of that supplementation. Team kind of touched base on that. I want to just go quickly to a little bit of the work we've been doing so far here. There's a lot of hype in terms of like the impact of seaweed on methane production. There's some work showing a huge reduction by this asparagopsis on methane emissions. That's all mostly related to the compound bromoform that's present in this asparagopsis that blocks that last step of methane production in the rumen. So there is work showing up to 98% of reduction. However, they can have high concentrations of heavy metals and iodine that can be toxic to the animals and can accumulate in meat and milk. So we got to be careful with some of those algae. There's some issues with toxicity of that compound bromoform, and if that kind of can carry to milk and meat. So there's some work being done in that area. So that's not going to be simple to get approval, even if it's a very effective compound. And we have very little work on animals yet, so there's more work being done. So we did like worked with like some researchers in Chile and in the US, Texas Tech University, and we started doing some screening of different algae. We used one species of asparagopsis and 3 other species of algae, and we compared to control diet without algae. And we saw relative to control that none of the algae we tested reduced methane production. And we actually had an algae that here, there's Macrocystis, that actually increased methane production. And it's similar to a lot of the work that has been coming out right now. There's many algae there that do not reduce and can actually increase methane production. Similar work was done by Dr. Stephanie Terry in Agriculture and Agri-Food Canada in Lethbridge, and shown that most algae that they tested from that did not reduce methane production. And there's one algae from Australia that have been shown in most of the work that reduce methane production. There's a lot of unknowns yet on that product. So it'll be interesting to see what comes out from that work in the near future. But I definitely don't think that that's going to solve our problem, or that's really the way to go so far. We also did a lot of work on biochar. We were probably the group that did most work on biochar. Like I was working with Dr. Tim McAllister in Lethbridge at this time, and we were probably the group that did most of the work on biochar for ruminants or for beef cattle, trying to reduce methane emissions. And we did not see any effect of biochar, and we still see people talking about that. But our work really clearly shows that biochar does not really reduce methane emissions. Just kind of want to bring the attention to that.
Thank you. I do need to say thank you for your presentation, because we are running out of time, and I need to move on to a panel discussion. This first question is for you, Tim. Are there unintended consequences from limiting the population of methogens too much? I would assume they serve some purpose in the room, and this came from the audience. Tim, if you can answer that, that would be great. Thank you very much for your presentation, Gabriel. Sorry, we're just running out of time.
Okay, I don't think I can turn my video on, but I don't know if you guys can activate me so that I can. Yeah, so definitely, we're a bit surprised. Some of those technologies that we talked about can reduce methane emissions by as much as 90%. In the past, we would have immediately predicted that those animals will go off feed, stop digestion, and it'll have severe negative consequences in terms of their productivity because of the methane being reduced by that much. We do see that still occasionally. I find it very hard to believe that we can achieve those levels of reduction without any kinds of long-term negative impacts on performance of the animals themselves, because of the evolutionary nature of how that microbial population is developed to use methane as the final hydrogen sink. It also taught us that we don't understand rumen stoichiometry in terms of hydrogen flow in the rumen completely either, because that hydrogen is going somewhere when we shut methane down that much. And we're not sure where. Some of it comes out as hydrogen gas, but there are other unidentified hydrogen sinks in the rumen. And we actually have a a grant in place now to work with a group out of the US and the New Zealanders in the Greener Cow program to try to figure out where that hydrogen is going.
Okay, Tim, I think you'll be able to turn your camera on now. We fixed the setting. So,
Okay,
Gabriel, this question is for you. There is a controversy about cattle versus fossil fuel methane emissions. Why do methane emissions from cattle production break down and get reabsorbed within the Earth's environment, whereas emissions from fossil fuels are not?
All like once that you have emissions and carbon in the atmosphere, all of that can be brought back to the soil, right? We're just saying that when we look at agriculture and livestock, that's part of a cycle, right? You have the plants that's bringing back that carbon from the atmosphere back to the soil, and then as those plants grow and cattle eat that, that carbon is being released again, but that cycle is constantly, and depending on management of the crops and the forages and management of animal, we can reduce the amount of carbon that's released to the atmosphere, and we can increase the amount of carbon that's stored in the soil. When we look at fossil fuels, we have just a release to the atmosphere, and there's no like, how do you bring that back? Unless you're connecting the fossil fuel production with a system that will be incorporating, like if you're planting trees or doing other things that will bring back carbon to the soil or retain carbon, you won't have that, right? So that's the point.
Thank you. John, we have a question for you. Do you suggest that achieving greater adoption of genomics in the industry requires a clear translation of benefits for breeders? If so, do you have ideas about how we can improve the translation of benefits and who should be responsible for this task?
Yeah, so great. That's a great question. So one of the things about genetic and genomic technology is that the technology first starts on the farm. It starts at conception, right? So, you know, it's a decision being made by the cow-calf producer and the breeder to use those genetics. Once that genetics is established, then, of course, genetic progress is permanent, right? In other words, we can't go. It's not like soil that can be, you know, the stores can be re-put into the atmosphere. It's permanent but slow, and so genomics speeds up that process. However, genomics, you know, genotyping animals, a large number of animals, can be expensive, and so we need to be able to incentivize that approach because it will improve profitability, sustainability, and reduce the carbon footprint of beef production. Who's responsible for that? Well, you know, we have some tremendous beef cattle organizations and dairy cattle organizations that do the general technology transfer, such as, you know, the Beef Cattle Research Council and the Alberta Beef Producers, etc. The dairy network, also the Canadian Dairy Network. However, there are, you know, key organizations, i.e., I'll give you an example, Livestock Gentech, that have the technology and create the molecular breeding values to also do that. So it would be a combination of all of those. It would be, you know, the science providers, it would be industry organizations, and in the area of cattle, our veterinarian service providers are so important, right? They're the ones that are right next to the producer, and they work with them on a daily basis, and they have many thousands of clients who own hundreds of thousands of cattle. So that's really, to me, the formula that gets them into, you know, gets this technology to be applied.
Thank you. Okay, Tim, we have a question for you. You focus more on the low-hanging fruit, specifically feed additives. However, unlike genetically enhanced production, these additives only reduce emissions rather than improve productivity. Additionally, some of these additives do not have regulatory approval. How can the adoption of these additives be incentivized?
Well, they definitely need to go through the regulatory process. That's number one. So we don't want to use any additives that haven't had regulatory approval. And it is, in some cases, there is a possibility that those additives will have added benefits in terms of improvements in feed efficiency as well. That's why I made the point that we need to assess each of those additives under the specific production systems of which they're being applied, because there's variability in the responses that take place. And so the benefits in terms of improvements in feed efficiency and that may not be expressed in all types of production systems. The other thing to keep in mind is that, really at this point, without that incentive in terms of improved efficiency, there's not a lot of reason to use these additives at this point. That may change if we start to put a value on carbon and producers are paid an incentive for developing technologies that will lower emissions from agricultural systems. Those kinds of things are being looked at, and policy people are developing those types of approaches, not only in Canada, but internationally as well. But when those will arise, how quickly those will be available, what the level of oversight will be, and how much you'll have to do in terms of an auditing process to demonstrate that in fact you're employing the technology properly and gaining the benefits that are associated with it. Those are all things that still need to be worked out. And if any of those things become too complicated or overwhelming for the producers to use, that'll also impede adoption of those technologies as well.
Thank you, Tim. We have a question from the audience, from somebody called Fitz. Anyone can answer this, so just jump in. Are there any enteric methane reducing substance that can be added to water that cattle drink? Who would like to answer this?
Well, they have looked at that as the one method of administering 3-NOP, but there's issues around concentration. So in terms of formulating diets and that and adding it at specific concentrations, John mentioned that as well. That's easier to do in a TMR than it is through administration of water as well, because consumption of water can vary substantially depending upon temperature and availability of other water sources that might probably be present in the pasture, the amount of moisture that's in the feed that the animals are consuming. All those things can act as variables in terms of trying to administer something directly through the water.
Tim, John, and Gabriel, we've heard that improving feed efficiency through genomic interventions has clear advantages for productivity and profitability. Can you speak more about the profitability gains that ranchers could see if they were to adopt strategies specifically aimed at reducing methanogenesis? And this is for any of you to jump in.
I'll talk first, and John can go after me, and he's more in that area of breeding, and he might contradict me here. But just a perspective here, I think we should think about this breeding for methane, and that's a way that a lot of people are looking into it. However, we can't forget about other things, right? That's just one of the traits that you should look. We have hundreds of traits of importance in cattle that we are looking and we're breeding for. And we need to work somehow that into our breeding. And even if we do that, it's going to be a slow process, right? It's going to be on the medium to long term. If we don't use more novel methods, like Tim kind of touched base, like gene editing or something, if we know exactly which genes are, and if it's a specific genes, and maybe to gene editing, we can do faster, move faster in that way. But so far to traditional breeding, that's going to be a bit slower. And even if we consider the gains we can have in 10, 20 years, they're not going to completely eliminate methane production. We have to understand that we can reduce maybe emissions or by animal for 20% or so. Maybe if you're really thinking an extreme, maybe 30%, but you will still have methane being produced in the rumen, right? We probably won't eliminate that methane production. But definitely that should be incorporated as one, or we should think in incorporating as one of the traits we look in our breeding.
Tim or John, do you want to add to this before I jump in for another question for Gabriel?
You're muted, John.
You're muted.
Yeah, sorry about that. So our group has measured tens of thousands, or let's say 15,000 animals for feed efficiency and more. Molecular breeding value, the use of genomics, speeds the rate of adoption. In other words, it improves the accuracy of your breeding value, and likely it decreases the generation interval, so you can make more rapid progress. The dairy industry has demonstrated that very clearly. So this is not precedent setting. The beauty about feed efficiency or residual feed intake, is the first thing it does is it reduces cost for the same amount of product. So it improves profitability. The second thing, of course, it does is it actually reduces methane. And then it reduces carbon footprint. So it is one of those technologies and traits that is really important. And we all realize that the cost of feeding cattle, livestock, is going up dramatically. And that is one of the things that's increasing the price of food for consumers and decreasing food affordability, which is becoming a real issue. So I view feed efficiency as one of the keys to work, because it has both benefits from a sustainability point of view, and it also, of course, reduces greenhouse gases.
Tim, do you have anything to add, or should I go to the next question?
No, the only thing I would say is it's important to keep in mind that the cow itself does not produce any methane at all. The methane comes from the microbes that reside in the rumen. So we need to keep that in mind. And there's a lot of things that influences the amount of methane that those microbes produce. The host is one of them, but it's not the only one.
And I also want to say that, like, I think RFI is just one of the methods of looking at feed efficiency, and I think there's a lot of like different thoughts on that, and we've been looking at other alternatives to improving feed efficiency that's different than RFI, and I think that they're important too.
Okay, so Gabriel, this is from the audience, and they put down themselves as anonymous, so I don't know their name, but they're asking you, can you give examples of teniferous forages that could be used for extensive grazing?
I think there's a lot of different forages out there that people are looking. It needs to be something that grows in your area, right? So that's applicable to where in the beginning, people were talking a lot about sainfoin. Our work shows that sainfoin is not a good plant to reduce methane production itself. It's good because it's a legume plant. It retains, it fixes nitrogen, and for the soil and the environment, it might have a benefit, but the methane produced by the animal itself, it's not a good plant for that. I'm not sure, Tim, if there is any teniferous plant here in Western Canada that you guys have shown that does a good job, but I know sainfoin, in my experience, hasn't really been good for that.
Okay, so I have a question from an anonymous person. The speakers seem protective of the industry and appear to push things to an either or, have the industry or not. Can we not have the discussion shift to what is enough based planetary boundaries and the ability for the planet to cycle greenhouse gases? John first.
Yeah, so that again is a tough one. I mean, essentially we're doing, you have to think about the activity that we're doing, and agriculture produces food, and it's been producing food for well over 10,000 years, and it's adapted with man. And so, that activity is important. In saying that, of course, agriculture needs to become more efficient, all aspects of it. And of course, over the years, it has done that. Some of the other activities where we're doing oil and gas industry, I mean, which is one of the major contributors to methane emissions, as we know, we can improve there as well, right? In terms of dealing with, the fugitive emissions from storage. So I think it has to be a more balanced approach. Well, I guess you might say, yes, we're all protective of the industry. We believe in the agriculture industry. It does some very good things for communities. I think one of the things that I view as missing from the discussion is that climate change is occurring, and it's going to continue to occur. And one of the things that I don't hear a lot of is how agriculture and other industries are adapting to climate change, right? Are we measuring different changes in terms of climatic variables? And are we adapting our systems, our plants, our animals to a changing climate? And I think that's the only other thing that I would bring to that.
Okay, so we're going to move to Tim here. Here's another question. How do environmental conditions and farm management practices affect the DNA-based selection score? Are there any specific implications for farmers in different regions or different production systems?
Yeah, sure there is. So the number one thing is to select animals for optimal efficiency within whichever environment you're talking about. And we've had those kinds of experiments going on where we've moved British breeds to tropical areas, and we find that none of them survive for the most part in that area due to the severe heat or different parasite challenges, those kinds of things. And so that's why it's very important to first do that, regardless of any impact on greenhouse gas emissions, because as we said, we're in the business of producing food. John made that point. Food is pretty critical for us. We're going to have a hard time surviving trying to eat our cars, so we definitely need food, and we would probably take food over our cars in many cases, right? We also need to look at a global perspective in terms of all of the sources of emissions. So agriculture is one of them. The fossil fuel industry is another one. The transportation is another one. Housing is another one. Like, we need to, as I said, pull out all the stops if we're going to deal with climate change. We need to look at every single area. And the difference is really between the ruminant production system versus the fossil fuel industry, is that the methane that the cow produced was previously carbon in the plant that it consumed. So that is why it's part of the cycle that occurred. Fossil fuel took carbon that was stored in the ground and released it into the atmosphere. So it's adding new carbon to that atmosphere. If we'd have never used fossil fuels and we only had ruminant animals on the face of the earth, we would not be dealing with climate change right now, because they would have just been using the carbon that's naturally within those cycles. They wouldn't have been adding new carbon to the atmosphere.
Thank you. Okay, so John, I have another question for you. Can you rank 3 great innovations in genomics that have a low adoption rate but can greatly benefit our cow-calf producers by lowering cattle feed intake and producing more beef and milk, please?
Yeah. So so the probably number one from the beef cattle point of view and the cow herd point of view, over about a 20-year period, the last 20 years, the amount of genetic diversity in our crossbred population, beef cattle population, has decreased. And what that has led to is fewer calves being born. And of course, all of us, I think it was, it was said very clearly that every cow should produce a calf every year. So that is one of the key things. So increasing the amount of retained heterozygosity or hybrid vigor in the cow herd is kind of number one, is in my view, from a genetics, animal breeding point of view. The second one, of course, is my favorite topic, which is feed efficiency or residual feed intake. You all know what I'm going to say. Feed costs are so important to the feeder cattle and the cow-calf herd. Improving feed efficiency is critical there. And then, the whole business, there are a whole lot of other traits that are available, and the application of multi-trait selection indexes would be important. Of course, those come from all over the place. They come from breed associations, from organizations, cattle organizations. So those would be my top 3 picks. If I was going to pick something from sort of like out of left field, the efficient production of beef on dairy calves right through to slaughter, that is a growing industry in Canada and a very strong industry in the US. And the use of genomic selection and genetic selection for those beef bulls on those dairy cows is also a high potential for reducing the carbon footprint.
Okay, so I have another question here, and all three of you can comment, but I'm going to ask Gabriel to start first. As one of the key takeaways from today's discussion, can we say that leveraging genomics to boost production efficiency and minimize waste represents a better business decision when compared to the use of feed additives? If you want to start first, please.
I think definitely we should be doing that, but I think it's a combined effort, right? I think we should look at all areas. I think feed additives is a part of the conversation, but not just feed additive, better management of forages, better feed formulation. Like, so we should be working in an integrated approach. So as an industry, we can make a faster improvements and definitely genomics is one of way you can do that, and breeding, and that area is so important.
Would anybody else like to comment on this question?
Well, I just agree with the point that Gabriel made, that it's back to my point that we've got to pull out all the stops. So feed additives are part of the equation. We should be using them. Breeding's part of the equation. We should be using it as well. And whatever other technologies we can find that'll help deal with the challenge.
Yeah, I would agree with him. It has to be all. Yeah.
Okay, so now we're going to go to the poll question. Thank you so much for this discussion, for your presentations. There's been so much great information here, and I really appreciate all of your enthusiasm and expertise. So before we conclude today's event, we have a poll question for the audience. After hearing today's discussions, do you feel there is a need for a better approach to communicate the effectiveness of methane mitigation strategies to ranchers? A, yes. B, no. C, maybe. Please answer the question, and then we will display the results. Just waiting for those results. Okay, we have the results here. And 90% of the participants said yes to adopting a better approach to communicating the effectiveness of these strategies to ranchers. 0% said no, and 10% said maybe to this question. So this concludes our event. Thank you, Tim, John, and Gabriel, for your time and the interesting discussion. To our participants, you will receive a post-event survey. Please give us your feedback. Please also go to the simpsoncenter.ca website, where the video of this special speaker series will be available, and to subscribe to hear more about our upcoming events and receive our monthly newsletter for more discussions based on research about Canadian food production. Thank you very much for joining us today.